Hey everyone, and welcome back to AI Paper Podcast. Today, we're going to be diving into a paper that tackles a challenge I think we've all probably faced at one point or another. You know, LLMs, they're amazing.
Oh, they are.
But man, are they resource intensive. This paper explores a potential solution to make them more efficient without sacrificing performance.
Right.
Which sounds almost too good to be true.
It does sound like a bit of a magic trick, doesn't it? But the authors of Towards Economical Inference, Enabling DeepSeek's Multi-Head Latent Attention in Any Transformer-Based LLMs, present a pretty compelling case.
So for viewers just tuning in, let's quickly break down what makes this paper so interesting.
Yeah.
The core idea is to address the memory hog that is multi-head attention, or MHA.
Right.
That's how LLMs understand relationships between words. But that key value cache it needs just keeps growing as the input text gets longer.
Exactly. It's like trying to run a marathon while carrying a backpack that gets heavier with every step. Eventually, you're going to slow down no matter how strong you are.
And that's what happens with LLMs, too. They get bogged down by this massive KV cache, leading to those slower processing times. And actually, the authors claim they've achieved a 92.19% reduction in KV cache size.
Wow.
On Llama 2.7b, with only a tiny 0.5% drop in performance.
That's incredible.
Imagine running those massive LLMs on your phone. That's the kind of potential we're talking about.
That's right. To put it in perspective, it's like shrinking a server room full of equipment down to the size of a laptop without losing any processing power. And what's really cool is they propose a way to adapt existing LLMs to use this new method rather than having to train models from scratch.
Yeah, it's huge. Nobody wants to spend months retraining a model just to make it more efficient. Okay, so they're not the first to try tackling this problem, though, right? The paper mentions a couple of other approaches.
It does methods like group query attention, or GQA, and multi-query attention, or MQA. They try to shrink the KV cache, but often at the cost of performance. Imagine trying to fit all the books from the Library of Congress into a small bookstore. You might save space, but you definitely lose some valuable information.
That's a great analogy. So where does this paper's innovation, DeepSeek's multi-head latent attention, or MLA, fit into all of this?
MLA aims to do what those other methods couldn't: compress the KV cache without sacrificing performance. It's like finding a way to store all those books from the Library of Congress on a tiny memory card without losing any of the content.
Okay, so that's a game changer. Now, I know we have a lot of technically savvy viewers, so let's get into the specifics. The paper introduces this framework called MHA2MLA. What's the core idea here?
MHA2MLA is all about adapting existing LLMs that are already trained on MHA to use this new, more efficient MLA. They're essentially proposing a way to upgrade these models without starting from scratch.
So that's smart. It tackles a real practical problem people face when working with these massive models. But how do they actually do that? It sounds pretty complicated.
It is, but the paper does a great job of breaking it down. MHA2MLA uses two key techniques: partial Ropey and low rank approximation.
Okay, hold on. Let's unpack those terms for our viewers who might not be familiar with them. Let's start with partial Ropey. What on earth is that?
Ropey stands for Rotary Position Embeddings. Basically, it's how the model keeps track of the order of words in a sequence. You can think of it like giving each word a unique timestamp based on its position in the sentence.
So it's like a positional awareness system for the model.
Yeah.
That makes sense. Why would you want to only partially use it? Isn't that information crucial?
You're right, it is important. But remember, the goal here is to shrink that KV cache. The Ropeys themselves take up space, so by strategically removing some of them, you can free up memory. It's a bit like using shorthand. You can convey the same information using fewer characters.
Interesting. It seems counterintuitive, but I'm starting to see the logic. The paper mentions a bunch of different strategies for this Ropey removal: high-frequency preservation, low-frequency preservation, uniform sampling, and something called headwise two-norm contribution. What's the deal with those?
They're all different ways of deciding which Ropeys to keep and which ones to toss. The idea is to find the sweet spot between saving space and retaining the model's accuracy.
So it's about finding that balance between efficiency and effectiveness.
Exactly. And the headwise two-norm contribution strategy turns out to be the most effective. Imagine each head in the multi-head attention mechanism as a specialist focusing on different aspects of language. Headwise two-norm allows the model to tailor the Ropey removal based on each head's specific needs.
It's like giving each specialist the tools they need to do their job efficiently without any unnecessary clutter. Clever. Okay, so we've tackled partial Ropey. What about this low-rank approximation business? That sounds even more complicated.
Don't worry, it's not as intimidating as it sounds. Low-rank approximation essentially uses a mathematical technique called singular value decomposition, or SVD, to compress the data. You can think of it like taking a high-resolution image and reducing the file size without losing too much detail.
Ah, so it's another form of smart compression.
Precisely. And what's particularly neat is that SVD allows the researchers to leverage the knowledge that's already embedded in the pre-trained model. They're not just randomly discarding information, they're using the model's existing knowledge to compress the data in a way that preserves the most important aspects.
Okay, so putting it all together, MHA2MLA uses this combination of partial Ropey and low rank approximation to essentially squeeze the key value cache down to a more manageable size.
Exactly. It's like they've found a way to make those LLMs think just as effectively, but with a much smaller memory footprint.
All right, so we've laid the groundwork for how this MHA2MLA framework works, but the big question is, does it actually deliver on its promise of greater efficiency without sacrificing performance?
Well, that's what we'll dive into next. The authors conducted a whole bunch of experiments to put MHA2MLA to the test, and the results are quite fascinating.
I'm definitely eager to hear more about those results. It sounds like they've potentially cracked the code on a problem that's been plaguing the LLM world for a while.
It might just have, but let's save that discussion for part 2.
Sounds good.
Welcome back to AI Paper Podcast. Before we went away there, we were discussing MHA2MLA, a framework that promises to make LLMs more efficient by shrinking that bulky key value cache.
Yeah, we talked about these really clever techniques, partial Ropey and low rank approximation, which sound really promising in theory, but I'm always a bit skeptical until I see the results. You know, did the researchers actually put this to the test?
Yeah, absolutely. They didn't just theorize, they experimented. They tested MHA2MLA on a whole range of model sizes, from a relatively small 135 million parameter model up to a massive 7 billion parameter one. Talk about comprehensive.
That's a great sign. It shows they weren't cherry-picking models to make their results look good. What benchmark did they use to evaluate performance?
They used Longbench, which is perfect for this kind of research because it's designed to test how well LLMs handle long sequences of text. Think question answering, summarization, those tasks where the KV cache really gets put through its paces.
Makes sense. If you're claiming to solve the KV cache problem, you better test it on tasks that are sensitive to it. So spill the beans. What did the results show? Did MHA2MLA actually deliver?
Well, remember that impressive 92.19% reduction in KV cache size on Llama 2 FEB&B we mentioned earlier. That wasn't just a theoretical figure. They actually achieved that in their experiments. And across other model sizes, they consistently saw substantial KV cache reductions, often in the 70-90% range.
Whoa, that's huge. A 90% reduction in memory usage?
Yeah.
That could be a game changer for running these models on devices with limited resources. Did they mention any specific applications that would benefit from this?
While they focused on the technical aspects in this paper, you can imagine the possibilities. Running complex LLMs on mobile devices significantly reducing cloud computing costs, even enabling entirely new applications that weren't feasible before due to memory constraints.
It's like suddenly all these doors are swinging open. But of course, there's always the question of trade-offs. Did this drastic reduction in KV cache size come at the cost of accuracy?
That's the amazing part. In most cases, they observed only a minor drop in performance, often less than 1%. It seems like they've managed to find a way to dramatically shrink the memory footprint without significantly impacting the model's ability to understand and generate text.
So to be clear, you're saying you can potentially shrink the memory usage of these LLMs by a huge margin, and they'll still be almost as good at performing complex language tasks.
Precisely. It's almost like having your cake and eating it too. You get the efficiency and you retain the performance. This could be a real turning point in how we deploy and utilize LLMs in the future.
Now, you mentioned that they tested different strategies for partial Ropey removal. Did they find that some worked better than others?
They did. Remember those 4 strategies: high-frequency preservation, low-frequency preservation, uniform sampling, and headwise 2-norm contribution. Well, it turns out the headwise approach consistently outperformed the others, achieving higher compression rates with less impact on performance.
I guess it makes sense that the most tailored approach would yield the best results. Can you give us a bit more insight into why the headwise method works so well? I'm sure our viewers who are deep in the LLM world would appreciate that.
Of course. You see, each head in the multi-head attention mechanism is like a specialist, focusing on different aspects of the language. The headwise 2-norm method allows the model to fine-tune the Ropey removal process for each head individually. It's like giving each specialist exactly the information they need without overloading them with unnecessary data.
So it's not just a blunt force approach, it's a more nuanced and adaptive strategy.
That's fascinating. It seems like a deep understanding of how these models work was crucial to achieving such impressive results.
Absolutely. It highlights the power of fundamental research. Sometimes the most significant breakthroughs aren't about building bigger and more complex models, but about finding clever ways to optimize the ones we already have.
Okay, so we've seen the experimental evidence that MHA2MLA actually delivers on its promise of efficiency without sacrificing too much performance. But what are the broader takeaways from this research? What does it mean for the field of LLMs moving forward?
Well, I think it points toward a future where LLMs are more accessible, more widely applicable, and potentially even more powerful.
That's a pretty exciting prospect. It makes me wonder if MLA becomes the standard for attention mechanisms. What kind of impact could that have on the development of new LLM architectures? Will we see a shift toward designing models with efficiency in mind from the ground up? That's a great question, and one that I'm sure many researchers are already grappling with. This paper definitely throws open the door to a whole new way of thinking about LLM design. It challenges the assumption that bigger is always better and encourages us to explore innovative approaches to making these powerful models more efficient and practical.
It seems like MHA2MLA is more than just a technical solution. It's a potential paradigm shift in how we approach LLM development, and that's what makes this research so compelling.
It certainly is. But before we get too carried away with speculating about the future, there's still plenty to unpack about the specifics of MHA2MLA and its potential limitations. That's what we'll delve into in our final part. We'll be back to explore some of the nuances and remaining questions surrounding this groundbreaking research.
Sounds good. Welcome back to AI Paper Podcasts. We spent the last 2 segments unpacking this really interesting paper about making LLMs more efficient. And honestly, my mind is buzzing with the possibilities.
It's certainly been a thought-provoking discussion. We've gone deep into the technical intricacies of MHA2MLA, this framework that seems to hold so much promise for the future of large language models.
We've seen how it tackles the memory bottleneck of traditional multi-head attention with those clever techniques like partial Ropey and low rank approximation, and the experimental results are impressive to say the least.
Those substantial reductions in KV cache size, often in the 70–90% range with minimal performance impact, are remarkable. But as with any new research, it's important to delve into the nuances and address those lingering questions.
Exactly. No research is ever truly complete. It just opens up new avenues to explore. So what are some of the areas that warrant further investigation based on this paper? What are those unanswered questions that keep you up at night?
Well, one thing that comes to mind is the potential impact on specific downstream tasks. While they achieved great results on Longbench, which tests a variety of language abilities, it would be valuable to see how MHA2MLA performs on more specialized tasks like machine translation or code generation. It's possible that certain applications might be more sensitive to even those small performance drops they observed.
Right, a 0.5% decrease in accuracy might not matter much for casual conversation, but it could be a big deal in a high-stakes scenario like medical diagnosis or financial modeling. It really highlights the need for task-specific evaluations.
Precisely. And another area that deserves further exploration is the interplay between MHA2MLA and other efficiency techniques. The authors mentioned combining it with quantization, but there could be other synergistic approaches that haven't been considered yet.
Yeah, I'm thinking about techniques like pruning or knowledge distillation. Could those be combined with MHA2MLA to achieve even greater efficiency gains? It's like we've stumbled upon a whole new toolkit for optimizing LLMs.
It's an exciting time to be working in this field. And of course, we can't forget about the potential limitations. While the authors have clearly demonstrated the effectiveness of MHA2MLA, it's still relatively early in its development. There might be unforeseen challenges that arise as it's applied to more diverse and complex models and tasks.
Right, there's always the possibility of unexpected edge cases or scenarios where the performance gains aren't as pronounced. And speaking of diversity, one thing that struck me as we were discussing this paper is the potential impact on accessibility. If MHA2MLA truly makes LLMs more resource efficient, could it open up the field to researchers and developers who don't have access to those massive computing clusters?
That's a really interesting question. It certainly has the potential to democratize access to these powerful models. Imagine if someone could run a state-of-the-art LLM on their personal laptop. It could lead to a surge of innovation from individuals and small teams who were previously limited by computational resources.
It's like leveling the playing field, giving more people the opportunity to contribute to the advancement of AI. That's a vision I can get behind. But with increased accessibility comes increased responsibility. We need to be mindful of the potential for misuse as these models become more widespread. How do we ensure that this technology is used ethically and responsibly?
That's a crucial point, and one that we can't afford to overlook. As with any powerful technology, there's always the risk of unintended consequences. It's essential to have open and ongoing conversations about the ethical implications of LLMs and to develop guidelines and safeguards to mitigate potential harms.
Absolutely. We need to be proactive in addressing these concerns and ensure that the development and deployment of LLMs is guided by ethical principles. But looking beyond the potential risks, I think this paper is ultimately a cause for optimism. It demonstrates that we're not just blindly building bigger and more complex models, but that we're also actively seeking ways to make them more efficient, accessible, and beneficial to society.
I agree. This research is a testament to the ingenuity and problem-solving spirit of the AI community. It's a reminder that innovation thrives when we combine technical brilliance with a deep understanding of the real-world challenges and opportunities that these technologies present.
Well said. I think we've covered a lot of ground today. We've gone from the nitty-gritty details of partial Ropey and low-rank approximation to the broader implications of MHA2MLA for the future of LLMs. It's been quite a deep dive. Thanks for joining us on this episode of AI Paper Podcasts. Make sure to check out the link to the full paper in the description and let us know what applications you're most excited to see in the comments. Until next time.